Thank you. So good morning, everyone. So my name is Gilles Orban de Xivry. I'm a researcher at the University of Liège in Belgium. I'm working with Olivier Absil as well. And today I'm very happy to present you the METIS, the ELT METIS instrument on behalf as well on the METIS consortium. So I thought first that I will actually introduce you or reintroduce you to the ELT. So the ESO Extremely Large Telescope. So this is a rendering of what is actually currently being built in Chile, in the Atacama Desert, not very far from the VLT that we just heard about. And yeah, well, just in a nutshell, I mean, so first of all, this is probably the biggest telescope that will be built in the optical regime. And then, yeah, in a nutshell, I wanted to just tell you. So this is a 5-mirror design. So you have this gigantic primary mirror. This is 39 meters in diameter. It's made of more than 800 segments that have to be precisely co-phase. And so they send the light then to a secondary mirror here, which is pretty large. It's actually 4 meters in diameter, upside down. Then you have a third M3 mirror that's there as well, of similar size. And then you have M4 and M5. M4 is the deformable mirror. It's a 2.4 meter diameter mirror. It's a very thin shell because it's only 2 millimeters thick and has more than 5,000 actuators on its back that you can then deform this membrane at 1 kilohertz. So this is really a piece of technology. And then you have M5 that's on the side. That's a tip-tilt large mirror as well that will send the light on the Nasmith platform. So now let's just play this out. So the light now here is here on M2. Then if we play that out, then it goes to M3, M4, M5, and then to the Nasmith platform. And here you can see this big annuli here, structure, is actually what we call a prefocal station. Display the interface between the telescope and the instrument. And that's the role of it is actually to deliver a good image quality. And so that essentially means it has to control M1 and control the telescope before it delivers the light to the instrument. Here, METIS. So what is METIS? It's the midi-infrared ELT imager spectrograph. This looks like this. It will weigh about 18 tons, like 3 big elephants. So that's massive. It's actually made of mostly this big cryostat that's hanging here. And I mean, most of the key optics is in that cryostat that is cooled down between 40 and 70 Kelvin. So METIS is built by a large consortium of 12 partners, 12 institutes. 10 of them are in Europe, 1 in Asia and 1 in US. And we all have our expertise and our work packages. But of course, it's also, it's a great team, but a lot of effort as well is put into actually coordinating this effort and making sure we can deliver this on time. So if you like numbers, two numbers maybe. So the hardware budget is on the order of 25 million euros. And in terms of labor, this is about 700 FTEs. So what is METIS going to deliver actually? So here you have summarized more or less all the modes and what it will offer. So you have on this plot on the x-axis the wavelengths and on the y-axis the resolution. So down here, it's very slow. I have to get used to this point. You have 2 imaging channels, so it's the resolution of 1. You have in the L and M band, so this is going from 3 to 5 microns roughly. And then you have another channel in the N band that is going to 8 to 13 microns, roughly. Then you have a long slit spectroscopic mode here with medium resolution. And then up there you have the LMS, what we call the LMS. This is the LM spectrograph, and that will provide a very high resolution of 100,000 in resolution. This is actually an integral field spectrograph, so you will have this resolution on a field of 0.6 by 0.9 arc seconds, where on every pixel you have this very high resolution. So all those modes, will work at the diffraction limit of the ELT. That's very important. That means part of the METIS, we have also a very good performing AO wavefront sensor, a pyramid one, that will control the M4 that I've introduced before. And in blue, you have the modes that will also have coronagraphic capability that I will describe in more detail after. Okay, so how does it look like? In a nutshell, you have here a block diagram of what it is. In blue, this is the part that's inside the cryostat. And in red, you have what we call the warm calibration unit that we use in daytime to calibrate the instrument, for example, the spectrograph. But we don't use, of course, that when we go on sky. So you have the light going from the ELT, entering the cryostat here through this window. And what we have first is what we call this common for optic. That's provide, well, it's a lot of optic and provide many functionality that are needed and distribute the light to all the subsystems. So you have here inside the cryostat the AO sensor, this is the pyramid one. You have the imager that I described before and the LMS spectrograph. So if I remove the cover, I get something like this. It's probably the more complicated diagram that has been shown this week. So I'm not going to really describe all that in detail, but you have the circles and squares highlight the major focal and pupil planes. And just to give you a feeling, I mean, I describe just a few here. You have the first pupil plane with as well atmospheric dispersion corrector, you have a derotator, you have some pupil stabilization, you have a chopper mechanism, and so on and so forth. But I'm going to describe later on a bit in more detail the HCI modes, eye contrast imaging mode. Okay, what about the timeline? So actually, this is a 15 years project, and that's pretty long for a ground-based instrument, in fact. So we are well into this, let's say, yeah, path. And we've passed several milestones. Recently, we've passed FDR, so the final design review. That means we are now 100% into the MIT phase. So sorry, there's a lot of acronyms. This means manufacture, assembly, integration, and test. So we are building components. We're assembling them. We are testing them, and slowly building METIS. So I have here a few illustrations. I show mostly big metallic pieces. I could have shown as well a lot of optical components. But you have here the cryostat, or at least a big part of it. Here you have the cold imager backbone for the cold optics. You have the derotator there, and then the last image is actually we're getting ready for the system integration. So we are preparing a big integration hall in Leiden to do that. So that activity will actually start next year, and will span for about 3 years, because in mid-28 we hope that we will have a complete instrument that is fully tested in Europe, and then we can actually ship to Chile. And if everything goes well, that means we start on sky in mid-29. Okay, so now let me describe a bit better the eye contrast imaging mode. So you have here a somewhat simplified diagram of the light path. So you have the ELT primary mirror here with possibly missing segments that can be realigned. You have M4 to control, to correct for the turbulence. Then we enter the instrument. We have first a cold stop here, PP1. We have a derotator. We have another focal plane. We split the light between the near-infrared, so in blue going to the waveform sensor camera of the EO, and the mid-infrared light going to the instruments. We have a chopper. We have another focal plane, and then we select the light to either send it to the imager or to the spectrograph. So in terms of HI mode, we have actually 2 classes of coronagraph and 3 different possibilities that actually echo quite what we've seen early on this week. So we have first focal plane coronagraph based on the vortex. So it can actually be either be classical vortex coronagraph, where we have here, we place a vortex phase mask here in this plane, and then we have downstream Leo stop here. Or we add as well a ring apodizer in the upstream pupil. You have here a picture here where you have an amplitude apodization here with this gray big annuli. And here on the right, on your right, you can see on top, this is the normal PSF we will get. There's actually, well, the image here is saturated. You have the classical vortex and then the ring apodized vortex coronagraph. And you can see that thanks to the apodization, we can strongly suppress the diffraction that is actually due to the central obscuration of the ELT. And then the other type is actually that we have is pupil plane coronagraph using apodizing faceplate, and in this case we use we place this component now in the pupil plane, actually the Leo plane here, and well in our case it would be a vector PP. That means we will have 2 replica of this PSF with a D-shaped dark hole. So the vortex chronograph can work, well, we have 5 of them, but they will be offered in L, M, and N band in imaging and spectroscopy, and the APP will be offered in L and M band. So those 3 classes of chronograph that provide you different trade-off between the throughput, contrast, and robustness to aberration. So that's really echoing what we've learned earlier this week. So we are building those components. So you have here on top 3 pictures, so scanning electron microscope picture of our vortex phase masks. Those are actually annular groove phase masks. So you have this groove here, so concentric grooves that are etched onto diamonds. What did I want to say? So this is actually synthesizing this 4-pi phase run that we need. Yeah, we have ring apodizer. So this actually recently received in our lab. So this is quite a big piece of optics. It's 80 millimeter. And you can see that there's this gray annuli here that's actually providing this partial transmission that we need. And that has been manufactured by actually depositing chromium microdot on it. Yeah. So it looks orange in the optical, of course, but in the mid-infrared it's pretty, of course, transparent. And then finally, the grating vector APP is also currently being built in Japan in collaboration with Nova. Yeah. All right, so let me now switch a bit of topic of something that is very important for the ATI performance is actually so wavefront control. We also have learned that this week. And here to summarize a bit well, all the flow in the sketch here. So we have the light coming from our object entering the atmosphere. We have dry air seeing, so the turbulence, and we also have water vapor introducing some additional aberration. I'll come back to that. So that the light enters the telescopes. Then we have the first module here, the adaptive optic module, that measure and try to correct actually for the dry air seeing. So. And then we have the light, the channels, well, the scientific channel going to the instrument, and we have additional optics there. And those are the additional optics may introduce what we call non-common path aberrations, and that means we need to somehow as well being able to measure them through focal plane wavefront sensing to correct for them, by dialing that into the AO. So METIS will actually be pretty much extreme AO system because it will provide more than 90% strail in all of its bands. And when it comes to NCPA, this has been strongly minimized by design, by the optical design. And as well, we are in a very controlled environment. So we are on an split platform, so it's gravity invariant. We are inside a cryostat, so we are at low temperature and pretty much vacuum. But we still need focal plane wavefront sensing because we still want to measure what we have in the focal plane. And one of the big challenge actually that we will face is water vapor seeing. So this is the fact that we have water in the atmosphere. This is not really a new discovery, but we have variable column density as you look over your primary mirror. And this variability means that, well, water vapor has some given refraction indices, and that means it introduces aberration. And the real problem is that this aberration is pretty chromatic when you compare what is measured by the AO in K-band at 2.2 microns and what you measure in the mid-infrared at 3.5 or 10 microns. So this chromaticity will be a big challenge because the adaptive optics is not seeing the same things as what the science camera is seeing, and so cannot correct for it. And so we classify this as being NCPA, although technically it's not really. Okay, so yeah, well, so we try to quantify this this amount of water vapor seeing we will get, and by using actually VLTI data, because in some configuration you get something that's pretty much cover as well the size of the ELT pupil. And so we try to quantify this amount by comparing K-band to N-band measurements. And so what we get is something like this. Let me see. Yeah. So this is after actually measuring and now introducing this in simulation just for illustration purpose. So on the left is what you will get if we had only dry air seeing. So that's the outcome of your adaptive optics simulation. And so what you see is mostly high spatial frequencies here, and for a total amount of 100 to 140 nanometer RMS. Now the middle panel is in L band, and we have an additional now 25 or so nanometer due to water vapor seeing, and you barely, well, visually can't see the difference, so it does make a difference. And then on the right is in the N band, so around 10, 11 microns, and here we have an additional about 300 nanometer RMS of wavefront error, and so it's completely driving now, well, the wavefront error. And moreover, as well, it's mostly low spatial frequency, so it will have a strong impact on contrast. So we need a mitigation strategy, and that means we need good performing focal plane wavefront sensing solutions. And so we have two algorithms that we are developing. The first one is to control pointing, so tip tilt basically, onto the vortex coronagraph. And for that we have an algorithm called CASITS that we have also already deployed on many ground-based instruments. And so we are confident we can achieve an accuracy of about 0.1 lambda over d at 1 Hertz or so. And so this algorithm actually is we have an illustration here. So it's really tailored for the vortex coronagraph because the response of the vortex with tip tilt is something that's non-linear. So this illustrates you and with VLT area simulation actually here. Now for higher order modes, this is a bit more challenging, and what we are proposing is to use an asymmetric LEO. So you have here a possibility of what this stop could be. An asymmetric because we have placed these two big bar, this big semi-bars, to actually encode enough information in the focal plane. So if you have a central symmetric pupil, you have ambiguity in the focal plane. The best example is focus. You cannot distinguish between positive and negative focus. But if you break this symmetry, you actually encode enough information that you can do focal plane wavefront sensing directly with your science image. And here we propose to do this by placing this mask in the LEO plane so that we don't degrade too much the chronographic performance. But then we don't have analytical, neither linear solution, so we resort to deep learning actually to perform this reconstruction. So we've now developed that, and here I'm going to show a small simulation in the N band where we correct at 10 Hertz 20 zonic modes. So you have on the left here the science image, and then you have the input aberration, and you will see the applied correction. So very quickly converge, so you get the characteristic diffraction, well, PSF that you will get behind the vortex. And you can see that the applied correction, well, we are able to follow the low spatial frequencies pretty well. Okay, so now let me move, I'll zoom out a bit, whoops, sorry. Zoom out a bit. Something is pretty, has been and is pretty important for the development of the HI mode is actually to be able to predict the performance and support the design of the instrument through simulation by tolerancing and by understanding what is really affecting our HI performances. So for that we've developed a package named IPS. It's also available on GitHub. I mean, we developed that for METIS, but it can be applied for other instruments. Where, well, it's actually a complex wrapper around proper. This is an optical propagation library, pretty much similar, well, not similar, but comparable to HI-Pi. And then we have also VIP here that we're using for HI post-processing. And so what we do in IPS, we actually do a model of METIS, of the chronograph, that we can now play with. We can introduce all kind of effects. And then what we give it to it, it's a lot of phase screens. We propagate through the instrument to obtain post-chronographic PSFs. And then we add the photometry, and we basically create a mock observation, and that we reduce, and we can produce contrast curve. So that rely on heavy adaptive optics simulation, because we want typically to actually do mock observation of 1 hour observation. So it means we actually need to run very long EO simulations. That can take several days actually. So here's the end result that we will get. So you have this contrast curve, so as function, contrast as function for angular separation. And so the floor here is set by the AO, the adaptive optic residuals. So this is the black curve. And then we can add effects on top of that. So the mauve curve is what happened if now we have some pupil drift. The red curve is what we add now amplitude errors due to Talbot effects. And the orange curve now is what happens if we add non-convergent path aberration. And the green curve is now if we include all those effects together, and that's what is our best expectation in the moment in terms of contrast. And that means we will reach, we should reach a contrast of 10 to minus 5 at 0.1 arc second. And the blue curve is a degraded case where we will be having a missing flow of segments, and as you can see from this curve is something we certainly want to avoid. Now, how does METIS will compare to 10-meter class telescope on sky? So this blue curve now is well, it's the same as before, except that now we simulate a 6 magnitude star, and so you have also the background flow here. And all the other curves are actually obtained on sky. So you have NACO, NIR2, LMR CAM, and recently as well ERIS. So they have slightly different integration time, field rotation, and magnitude, but essentially it tells you that they all lie in this regime, and with METIS we'll really do a big leap, and is in this gap that we'll hopefully make a lot of discoveries. Okay, so just finally, before going to some science, but METIS into a ELT context, so actually there will be 3 first light instruments on the ELT. The first one is Mikado. This is a near-infrared imager and spectrograph. That's supposed to come first in 29. So shortly after we'll have METIS, and then a little bit later we'll have Harmony, which will be a visible and near-infrared integral field spectrograph. So now I wanted to go through a couple of the key science cases that we want to address, and that's going to echo a lot of what we've learned this week as well. So of course I'm going to focus only on direct detection of exoplanets and characterization of them, and METIS is actually a multi-tool instrument. It's going to address a variety of science topics, so just keep that in mind. So the first thing we want to do is to look at the handful of objects we will be able to look at that have dynamical mass measurement from astrometry and radial velocity. And thanks to that, we can calibrate our model to later use effective temperature luminosity to have mass measurement from direct imaging. But then by looking at known system, and again we have here HR 8799. I mean, if we get those kind of fantastic images, then we can dial this into the spectrograph and do all kind of analysis. And we've seen this diagram already several times. So we can, for example, via Doppler imaging, look at clouds and spots on the surface of giant planets. Of course, also atmospheric characterization and all kind of those exciting science here. Now because we'll have a better resolution and angular sensitivity, we should be able to look into the regime of this 1 to 10 AU, where we expect to have a peak of occurrence rate, at least as known from RV distribution. And hopefully there we can make a lot of discovery. So we have some colleagues that are actually looking in the detail of that. So which stellar association we should look at, and what will be actually the yield of that. So this blind surveys as well echoing some presentation yesterday. So now probably one of the very exciting but as well very challenging science case would be actually do we have a shot to look at rocky temperate planet with METIS? And we might have one with on Alpha Cent, for example, so in the N band. So you have here a simulation where we have injected one Earth-like planet at about 1 AU and a warmer planet at half the distance. And you can see that if we don't have water vapor seeing, you have a clear detection within 5 hours of observation. Now with water vapor seeing, the signal is completely lost in a sea of speckle, and so that tells you we have a big challenge. And so our ability to correct for this water vapor seeing is going to really be a driver for that, but not only our ability to correct for it, but as well to forecast the amount of water vapor seeing we'll have. Because here we have a comparison here. So what I shown before is actually assuming this orange curve, but if we have now 4 times less water vapor seeing, then we might have a shot to actually detect that. But all those curves actually assume we are doing the correction. Okay, so how many of more targets we might have? Only a few of them. So in the paper, Rory Burns tried to look into that and predicted that first on Alpha Cent we have a 50% chance of actually detecting a temperate planet. And then you also look at trying to design a mini blind survey of 1/9 around the 6 closest stars, and the yield will be about more than 1 temperate mini Neptune. Okay, so I'm running out of time. We're going to go a bit quick, but of course, another thing is about characterization of a rocky planet. The best shot might be Proxima b, where we combine HCI and the high spatial resolution. So if you have here a simulation of Proxima b, and there might be a few more objects. So this study actually looked into that, but this is really just a very few. So I'm going to finish on this one, where this gives you a kind of a broad picture of what the mission, the upcoming mission, is going to give you access to the habitable zone. So yeah, I described METIS. It's really going to be really few of them. Then we'll have to wait for the second generation instrument, so PCS on the ELT or GMAG-RX that you will hear after me, or MODIS. And then if you want to look at the habitable zones of solar type star, we'll have to wait for HWO and life. So this is really my final slide. And so this is a recent picture of the ELT, so you can see that it's really progressing nicely. And yeah, well, we just have 5 more years to go, so it's long and actually very short. So, but finger crossed. Thank you very much.
Great. Yeah.
Hi, I'm Rachel Bounzerman from Santa Cruz. I'm very curious about the water vapor seeing. What is it? How do you sense it and how do you correct it? Is it like regular seeing or something totally different style of adaptive optics or not even adaptive optics?
Yeah, I'm not sure I got the last part of your question, but I'm going to try to answer, yeah. So dry air seeing first is pretty achromatic. I mean, it's not completely achromatic, but typically, sorry, we can ignore that. So the problem with water vapor, as I said, is the chromaticity, and of course that you have a variable distribution above your primary mirror. And the fact, well, the variability, the non-uniformity of water distribution above your primary mirror means that you have aberration, and then the refractivity of water and the fact that it's variable with wavelengths give you a chromatic effect. And so when your wavelength sensor that is working at 2.2 microns, and then the science channel now, is, for example, in N-band works at 10 microns, you have a big gap in wavelengths, and this leads to very different refractive indices, meaning that you have a different level of aberration. And so that means that what the AO is seeing is not what the science channel is seeing. Yeah, right. So I don't know if you've...
Is the plan to have like a 10 micron wavefront sensor and somehow be able to correct at the right color, or?
That would be great. So as you've seen, the design now is pretty much frozen. And so we actually really understood the depth of the problem a bit late in the project. And so the mitigation strategy is to use focal plane wavefront sensing, so to use the science images to do as best as we can. Yeah.
Thanks.
Other questions? Another one down here.
Hi, I'm Maria Vincent from Institute for Astronomy, Hawaii. Thanks for a great talk. I was wondering how, I think it's called Morpheo, the multi-conjugate AO and for ELT. How is that going to be working with, is it going to be working with METIS, and if so, how are they going to work in conjugation, I guess?
So Mikado is going to, well, to try first, we'll have first a single conjugated AO, and later there's Morpheo, which is multi-conjugated AO. But so METIS has its own AO sensor, and it's a single conjugated adaptive optic system, and a superior emitter wavefront sensor. So it's basically because all the science we're going to do is pretty much on axis, or very close to it. So we don't have a very big field of view, and so and we only use as well a natural Guy star as well. So that's the other effect.
Okay, thank you.